In this video, I'll be talking about a method to solve a Laplace equation. The method is called successive over relaxation, which is used for elliptic, boundary, or partial differential equations. In this case, we're going to look at Laplace equation, that is d squared phi dx squared plus d squared phi dy squared equal to 0. So there are two differences between this equation and the one we've seen so far, particularly the heat equation or the diffusion equation. In Laplace equation, which is in this equation, we have two independent variables, x and y. The derivative on both x and y is the second derivative. So this is in contrast to the heat equation where we had time instead of y, and then we had a first derivative on time. Now here we have the second derivative on y. So these are the two differences. Instead of time we have y, and then we have, instead of the first derivative, we have the second derivative. Alright, so let's see how we can solve this using successive over relaxation method, or SOR. So we're going to apply the central differencing in the first and the second term. From page 83, if you look it up, you see that for d phi dx we can write phi I minus 1j minus 2ij plus I plus 1 comma j divided by del x squared, which is the discretization of the first term, and then plus ij minus 1 minus 2ij plus ij plus 1 divided by del y squared, which is discretization of the second term. So by looking at del x del y, you see that we are using basically a grid. Let's assume this is the y-axis pointing down with j index, and this is the x-axis with I index. I have an increment along the x-axis, del x, and an increment along the y-axis, del y. So I goes from 1 to n, let's say, from left to right, and j goes from 1 to m, from top to bottom. Alright, so now to solve this differential equation, or the discretized form, we're gonna solve for phi ij, move it to the left, and then move everything else to the right. So in that case, if you do the math, you see that phi ij from this equation becomes equal to del x squared times ij minus 1 plus ij plus 1 plus del y squared times I minus 1j, I plus 1j. And the whole thing divided by 2 del x squared plus 2 del y squared. And the factor 2 here comes from the prefactor 2 from the original equation here and there. Now to go from here to there, we actually multiply through by del x squared, del y squared. And that's why the coefficient for phi ij becomes del x squared plus del y squared, and then multiply by 2. Imagine we have boundary conditions of this form. We have phi equals 0 on 3 edges, and then phi equal 1 on the left edge. And the goal is to find phi for intermediate points or inside the domain. For simplicity, let's assume del x and del y are equal. So in that case, we can go ahead and simplify equation 1. We can cancel out del x and del y from numerator, and del x squared del y squared from denominator. Alright, so if you cancel them out and then add 2 and 2 and down the stairs, you get 1 over 4 I minus 1j, I plus 1j, I j minus 1, ij plus 1. Okay, so this is equal to phi ij. Now how I can solve for phi ij? Well, you know, I need to know all these 4 terms to get phi ij. That means if I start with an initial guess, let's imagine I guess all the phi values for all the grid points, excluding the boundary points. Boundary points are given, so I cannot guess. For the intermediate points, let's assume phi is 0 initially. Then I put all zeros for these terms and then calculate phi ij. Now this ij can vary from, let's say I from 1 to n and j from 1 to n. Basically, I have to calculate this, or equation 2, for every grid point inside the domain, okay, excluding the boundary points. This is one sweep. You need to know what is the tolerance to basically calculate how many times you have to sweep through the grid. Every time you sweep over the grid, you find a new Phi-ij. If you compare the new Phi-ij with the old one before the sweep, you find the error. Now the tolerance limits that error. Let's say if the tolerance is 10 to the minus 3, then you have to sweep over the whole grid as many times as you get the error on each grid point less than a tolerance. So I'll show you in the next video how we can implement this condition to limit the error using VBA. Now let's, as a final point, let's look at how we can accelerate the convergence of this iteration. So we know that to get Phi-ij, we have to iterate over all the lattice point or all the grid points many times unless we get the tolerance satisfied. To accelerate the process, what we can do is, instead of having Phi-ij on the left in equation 1, I can write equation 1 with uij, a new variable, on the left. So now I have uij equal del x squared Phi-ij minus 1 plus Phi-ij plus 1 plus del y squared Phi minus 1j Phi plus 1j over 2 del x squared plus 2 del y squared. In other words, on the right side I have Phi's, on the left side I rename it as u. It's uij. Now I relate Phi-ij to uij as follows. Phi-ij is equal to, this is new Phi-ij, is equal to old Phi-ij plus some factor which is called successive relaxation factor, or SRF, times the difference of uij and Phi-ij. So again, this Phi-ij is old, this Phi-ij is old, you calculate the uij, and then the result of this will be new Phi-ij. Now, if SRF is between 1.2 and 1.5, we get the most accelerated convergence. If SRF is equal to 1, then Phi-ij and minus Phi-ij cancel out. On the right side, you get only uij, and this means Phi-ij is equal to uij, which is exactly equal to equation 1. So if SRF equal to 1, we don't get any acceleration. To get acceleration and convergence, SRF need to be more than 1, and specifically between 1.2 and 1.4. All right. Now, I forgot to mention that if the boundary condition is not in this form, which is pretty much like what you have to do in problem 3 of homework 7, we need to do a little bit different. Now assume the boundary conditions are in the form of derivative. Okay, for a specific case, let's consider I have this domain, I have this grid. On the right side, or on the east side, I have d phi dx equals 0, and I'm looking at how I can impose this into my successive relaxation method. So for intermediate points, nothing has changed. For intermediate points, we still use our successive relaxation method with accelerated factor SRF. Basically, using Phi's, we calculate the u, and then from u, we calculate the new Phi for the intermediate points. Now, for the boundary points, if the boundary points are given as like Phi-ij equal to 1 or 0, then we can use them exactly. So I don't need to even iterate over the boundary points, maybe over here, if the Phi's are given. If the Phi's or if the Phi is in the form of derivative like this, I use finite differencing. In this case, because I'm sitting on the east edge, I need to use backward difference. And because this is along the x, because this is d phi dx, I have to use backward difference along the x, keeping y index fixed. That is to say, 3 phi n comma j if I'm sitting at I equal n. Let's say this is I equal n. Then phi n comma j times 3 minus 4 phi n minus 1j, which is the point before. Let's say this is point nj, this is n minus 1j, this is n minus 2j. All right, so that's minus 4 phi n minus 1j plus phi n minus 2j divided by 2 del x. And this has to be 0. This is actually the discretized version of d phi dx. You set this to 0. That means numerator has to be 0. And from here you can solve for phi n j, which is 4/3 of n minus 1j and 1/3 of n minus 2j. In other words, you're relating this point to 4/3 of this point minus 1/3 of that point. Okay? So this is d phi dx. You can similarly do the same thing if d phi dy is given, let's say on this edge. Then you have to go along the vertical lines and pretty much do the backward difference or forward difference depending on either you're on the north side or south side, west side, or east side. All right. So this was successive over relaxation. I hope you learn how to apply different boundary conditions, specifically how to use successive relaxation factor SRF. In the next video, I'm gonna talk about how to implement this in VBA and how to use that script, particularly to solve problem 3 of homework 7. So stay tuned, and thanks so much for watching.